Hi everyone, my name is Duygu and I am a PhD candidate at Stockholm. Today I will present my research topic, which is holistic building performance model with semantic web technology. During the presentation, I will briefly mention performance-driven design, building performance models, ontology, CBIM project, and this research hypothesis with expected contributions. Identifying and assessing total building performance analysis is a sophisticated task for design teams, since they must simultaneously consider and balance objective and subjective factors in different performance domains, such as energy, acoustic, lighting, air quality, circulation, and safety. I would like to give 3 examples of building performance analytical models to underline the different performance criteria. For the lighting analysis, firstly, the building model is generated. Then, calculation grid points should be placed on the building model to simulate lighting level on the surface. If the illuminance level doesn't meet the requirements, the lighting fixtures should be modified by the design teams. For the natural ventilation, some of the important parameters are building opening size, locations, as well as outside weather conditions like air temperature and air velocity. We can see one of the air circulation analyses conducted by computational fluid dynamics software. Especially in these pandemic days, air circulation analysis for commercial buildings is getting more important to simulate the dispersion of air particles like COVID-19 viruses and to see the indoor air quality. The last example is for acoustic analysis. In this performance analysis model, there is a one-point sound source. Based on the features and placements of this sound source, we can see the dispersion of the sound waves through the distance. Therefore, the building performance assessment needs integration and optimization of various quantifiable performance criteria from different domains. When you look at the design process, the first approach has been a conventional design process. The conventional design process starts with an architectural model. After the architectural model is completed, the design continues through the other disciplines. Also, the conventional design process has sequential design stages, which are conceptual, preliminary, developed, and detailed. There is only one iteration between preliminary and conceptual stage. Therefore, the conventional design stage limits the ability to evaluate and optimize building performance comprehensively. Further, the building performance-driven approach with integrated design process has become prominent while evaluating building performance and making an efficient design. This approach brings 2 developments. The first development is that the experts on architectural, structural, and MAP files interact at the beginning of the design stage. Secondly, there are iteratively activity loops to fit building performance evaluation and optimization during the design stage. Another saying, this design approach forms on circularly iterative activity design stage. For example, the initial building service and systems are created in the conceptual design. After then, the design goes to preliminary stage. In the preliminary design stage, the performance analyses are conducted. If the analysis results do not meet the performance targets requirements, the design turns back to the conceptual design stage, or some improvements are done in the preliminary design stage. Same thing also happens following space. As a consequence, total building performance assessment needs the creation of multiple performance models by using computational aided drawing tools and different performance simulation softwares. Different drawing and modeling techniques have been developed. Eventually, the drawing and modeling techniques shifted from graphic-oriented to object-oriented programs. Two-dimensional drawing tools use 2D polygon shapes based on Cartesian coordinates. Therefore, these tools provide only geometry information for building performance models. Three-dimensional modeling tools use 2D polygon shapes, 3D constructed solid geometry, and bounding box representation. Therefore, these tools support geometry and space information for building performance models. Also, object-oriented programming programs are based on manipulating data packets among predefined object classes, which provides an unique advantage in data sharing and maintenance. Thus, object-oriented modeling has enriched physical and functional building information input to building models. This model is also called Building Information Modeling, BIM. The required information for building performance models are provided by BIM models. Further, industrial foundation class and green building studio data schemas have been released to enable interoperability between diverse software applications by exchanging building information through the building lifecycle. However, they have some limitations. These data schemas have a deficit of definition in their libraries and associated standards. As a result, they leave domain-specific objects and elements out. Consequently, BIM applications and analysis tools have their native models. Also, these data schemas have restricted information, semantics, and knowledge coming from modeling concepts and requirements. As a consequence of that, when extracting data from the building information model and data schema, the outcome is generally delivered with inaccurate, incomplete, or false information. Based on these limitations, a new approach is suggested as ontology using semantic web and its techniques. The semantic web provides an environment where the data and service on the web can be semantically interpreted and provided by machines. Protocols and language of the semantic web comprise three layers. The bottom layer shows the protocols that refer to resource. The middle layer is for necessary language to exchange resource description. In resource description framework, RDF, and/or extensible markup language, XML. But the upper layer displays the querying method with descriptive language like Sparkle. Also, encoding and constructing data with ontology web language, OEL. Subsequently, encoding and exchanging logical rules by rule interference formats, RIF. Consequently, the semantic web technologies heavily rely on a formal ontology to structure data and model semantic content. For a more deep looking, so what is an ontology? An ontology is a formal specification that provides shareable and reusable knowledge representation. It includes syntax, as a common symbols and concepts. Semantics as an agreement about meaning. Taxonomies is being classification of concepts, which is also called hierarchy. Theory as being associations as relations of concepts. And finally, logical models that contain rules and knowledge about which relationships are allowed and make sense. I would like to give an example of how ontology includes these concepts. In the example, there are two individuals, Fred and Wilma. They are belong to the person class. We also know that a person is a member, so that the superclass of person class is the member class. Also, the root of each ontology is first the team class. We can see the hierarchy following this branch. Also, Fred works for the slate rock company, which belongs to the company class. And we can create a relation that a person works for a company. Also, we can create relationships between the individuals. For instance, Fred has a suppose who called Wilma. One of the logical statements based on this relationship is that Fred should know Wilma. Therefore, ontology supplies centrally structured and stored reusable knowledge from heterogeneous and decentralized systems. Since ontology consists of entities, classes, functions, and relationships between the classes, it can also reflect every change in the knowledge domain. We can also say that an ontology supports an extensible, dynamic, and reusable knowledge-based domain. Many researchers have been developed an ontology for buildings. For instance, ontology for managing geometry is suggested for geometric data integration for building objects. The building topology ontology is provided to explicitly express semantics between subcomponents of a building. Also, Saref, Dogonto, and Tinko are developed to facilitate smart applications and automation devices for building. Brick is generated to support spatial information, building systems like HVAC, lighting, and sensor systems, as well as control and operational relationships. Lately, ISO-OER has been released to support standard ISC data schema via semantic web technologies and linked data application. ISO-OER can also utilize in building performance domain. Furthermore, sim model ontology is suggested for designing energy models to make building simulation data more interoperable. Key performance indicator ontology is created to link performance indicator information and data for thermal control. Current building performance ontologies are mainly based on the energy domain and integration of application-specific smart devices in buildings. Therefore, a multidisciplinary combined building performance ontology is absent. So, why is the combined building performance ontology needed? It is needed to achieve a more robust building performance assessment by analyzing, interpreting, and optimizing performance intent and requirements at the beginning of the design stage. Also maintain them through building life cycle. To sum up, shared building information strategies have been moving from traditional data exchange strategy to a linked building data approach. In the traditional data exchange strategy, information should be interpreted and converted manually Therefore, it needs rework in all steps. In the centralized model strategy, even though information stored in a central model, while functioning, information exchange among softwares is hard to achieve. And slightly, a link building data approach is suggested. Different information resources are linked with this approach. And a management system operates this link. Even though a link building data approach supports an advantage of data integration and information sharing, currently, no solid proposal exists for fully resolving interoperability problems using semantic web technologies. It means that at least there is no proposal that solves it any better than existing approach. At that point, as my colleagues previously mentioned, the cloud-based building information modeling project offers a new approach to resolve interoperability problems by considering design intent and collaboration, multidisciplinary collaboration in different domains. Also, the previous section, the CBIM frameworks, is explained very well, but I would like to explain it once again. The CBIM structure authenticity comes from 3 different segments having different duties. The first segment is CBIM ontology. The CBIM ontology integrates decentralized and heterogeneous data flows from different disciplines like architectural, structural, and so on. Also, it explicitly identifies and views semantic contents among different discipline-specific objects and relations. Thus, CBIM ontology facilitates interconnection between diverse different domains that also include performance domain. The second segment is CBIM engine. CBIM engine contains artificially intelligent semantic enrichment methods to initialize the determined object relationships from CBIM ontology. The last segment is CBIM database management system. The CBIM database management system enables local and cloud platform to store federated discipline-specific models, data schemas, and CBIM ontology in knowledge graph. It also supports different management system functionalities, such as simulation, so that we can maintain up-to-date models and perform simulation on demand. Under the CBIM framework, especially under the CBIM ontology, the research idea is to devise a holistic building performance ontology with object relationships and semantic web technologies to support, first, automated preparation of performance domain analytical models and optimization for the whole system by communicating with other disciplines. Second, automatic identification and establishment of semantic links between building model objects and building performance simulation tools, which enable two-way communication. Third, or lastly, encompassing interoperability to ultimately connect all performance domains, independent of file-based data exchange formats. Thus, 3 research questions arise. The first research question is that what information is missing, inconsistent, or supplementary in any data schema in isolation and across multiple performance domains and architectural engineering and construction disciplines. The second question is that what are the semantic contents into the internal data schema? The last question is that how can new semantic relations be set within and across domains to enrich semantic contents, represent explicit information derived from implicit information, and achieve fully interoperability. Based on these research questions, a research methodology is proposed. The proposed methodology starts with the problem identification stage. And the identified problem is that there is no holistic building performance ontology to serve determined scopes. Based on this problem, two objectives are different. The first objective is to determine a subset of performance domains, which aim to represent all possible performance disciplines. The second objective is to investigate, develop, and test object relationships and semantic enrichment in practical terms, covering performance domain and AEC disciplines. In the design and development stage, 4 activities are defined. The first activity is an interview with domain experts and reverse engineer software to reveal native data schemas. The second activity is to generate native building performance simulation models and internal data schemas in property graphs. The next activity is to identify and set intra and inter-domain semantic enrichment targets. The last activity is to establish holistic building performance ontology by applying a hybrid approach. The demonstration of validation step is for the performing a set of experiments to make sure that the holistic building performance ontology achieves all the determined scopes. And evaluation step aims to measure the effectiveness of the established holistic ontology by preparing an alpha prototype software. The last step is to disseminate our outcomes. Therefore, we also propose the research method. The proposed research method comprises of 6 steps. Firstly, building performance simulation software are used to produce internal data schemas and native analytical models by direct export or reverse engineering. Schema to graph conversion code for internal data schemas and parsing code for native analytical models are applied to obtain graph representations. The obtained graph representations are integrated into property graphs in RDF form. And also they are stored in the cloud. After then, the generalized semantic contents are ascertained for each property graphs using query methods to identify and set inter- and inter-domain semantic enrichment targets. The ascertained semantic enrichment targets are represented in blue line. Subsequently, a holistic building performance ontology is established by applying a hybrid approach. This hybrid approach combines the direct link in the property graph by using semantic enrichment and linked data techniques. Also, the creation of new relational graphs for connections by using rule-based interference and machine learning techniques. Lastly, a formal holistic building performance ontology under the CBIM ontology is constructed with logical statements by using ontology wrapped language and controlling with the reasoning. They have same modeling techniques for geometry and object placement, which are 2-dimensional polygon shapes, 3D constructive solid geometry, and bounding box representation. Also, they have the same simulation methods, which is based on analytical grease and propagation through air that occurs in indoor environments. When we look at their differences, actually lighting and energy domain required same information on space and room building elements. However, acoustic domain has slightly different information on these criteria. In the acoustic domain, the identification of enclosed surface geometry and interior surface is enough for performance models. When we look at the required information on material and building system components, we can see that they have totally different necessities. Therefore, we examined data exchange performance among these selected domains specific softwares. Data exchange performance is considered into two classes, which are geometry and object, also domain-specific data. For the geometry and object data formats, image format could be application-specific. For the 2D, 3D solid, 3D object and information would exchange among software in different file formats. Regarding domain-specific data, we can see that each software has its native binary internal binary data formats. Another important finding is on energy domain building input. The building input covers information on material properties, building elements, and openings, lighting, hedgeware, occupancy activities, and building functionality, which means that the building input data is in a heterogeneous data format. Therefore, it needs different libraries. Also, we found that GBXML data schema is a common data schema for energy domain. Since GBXML is the common data schema for energy domain, we examined semantic content, object properties, and relationships for lighting and acoustic domain. In the IFC data schema, there is no acoustic domain property entity. Regarding the object property, there are two acoustic domain properties, which are sound attenuation and sound generation, which belong to sensor class. Therefore, there is no explicitly identified acoustic domain properties, relationships, and entities in the IFC data schema. Same thing is also for GBXML data schema. In the GBXML data schema, there is no acoustic domain property entity. And also, there is only one acoustic domain property, which is assigned to ceiling building elements. Therefore, we can say that the property, the object entities, properties, and relationships for acoustic domain are not explicitly identified in the GBXML data schema. Based on these situations, we created unified modeling language diagram for acoustic domain by applying reverse engineering on Adeon software. We found 5 packages in Adeon internal data schema. I will show 2 packages in detail. The first package is data exchange package. The data exchange package allows importing predefined different file formats. There is a one object class, which is called import class, with determined enumeration data, which for import files. We can also see that the import class has Cartesian coordinate attributes and one function, which is reset coordinate. The visualization package allows in displaying, debugging, and opening 3D geometry and simulation results. In this package, there are two object classes. One or many individuals in display class can be associated with the debugger class. Also, the debugger class is associated with Open Graphics Library class. We are rendered by relationship. This research is on ongoing research. So we are in still the first step of the research method. However, I would like to mention about the expected results at the end of this research. The originator of this research proposal is the structure of a holistic building performance ontology to serve multiple different performance simulation domains and solve interoperability, data interference, and implicit data problems in three aspects. The first aspect is a domain-specific or application-specific information for semantic enrichment and BIM models after the exploration of multiple knowledge data sets. The second aspect is a high level of confidence about explicit and implicit data for stable and standard semantic content and object relations via semantic web technologies such as query methods, linked data, rule inferencing, and machine learning. The last aspect is automated preparation and updating of performance domain analytical models via holistic building performance ontology in cloud-based. Thank you for your attention.